So I'm Ying, happy to talk today. I'm a software engineer at Databricks. Today I'm going to talk about some of the things we built and some of the hard-earned lessons we had during serving large language models at scale. Let me change the slide. So some people might be surprised that Databricks serves large language models, and we actually do, and at a pretty large scale. In May alone, we have served more than 125 trillion tokens per month. This is spanning across customers such as Grammarly, Ipidata, Fox Sports, and a lot of different domains in their production systems. And also in a lot of Databricks AI products. We use our serving stack to power high concurrency scaling for fine-tuned models provided by our research team. So a lot of challenges may arise for serving inference at scale. One potential thing is GPUs are expensive and hard to come by. Even if you have a lot of GPU capacity, you have more demand that you can supply. So you need to make a trade-off between over-provisioning the GPU but have a very low GPU utilization and letting the GPU sit idle. Or on the other hand, if we don't scale the GPU fast enough to supply the demand, it may run into 5x errors and increase latency, which is not great. So we must be able to estimate this scale and provide rate limiting across different workloads and customers. Another challenge is that the engines, the models, everything change very quickly. So this is a very quick space to catch up, and you need to have a lot of optimizations as well. So this is a lot of code that is shipping every week. And we need to make sure that we have some robustness in our system to make sure that even if something wrong goes on or goes wrong in production, we can fill over and recover very quickly. The last consideration is that this is a large system. As we evolve the system, it may have more components interacting with each other. So a local issue may become system-wide failures and cause cascading issues. So we need to be able to pinpoint these and provide a holistic solution for these reliability issues. So starting by talking about capacity, the trade-off between over-provisioning GPUs, or maintaining good high availability or versus reliability. So starting from scratch, if we are serving a model, the easiest way to start with is to have several pods running in a Kubernetes cluster. We'll have the models of different sizes. For example, model A may be a model that requires 2 GPUs, and we may have different number of replicas of these models depending on the demand. For example, maybe B is a larger model, but not many people are using it, so we aren't scaling it up. And we may still have some headspace in the GPU cluster that we can scale up on. So across like this serving engine, we need to make sure that there is some reliability across this so that this can be running and be maintained by Kubernetes and our infra to recover. And on top of the model deployments that runs the serving engines, we may also have some router that is able to do cache-aware routing or session-based routing and do load balancing between the pods. On the other hand, the autoscaler will be able to control the scale up or scale down of the model pods so that we can scale up or down depending on the demand. And this is what we call the data plane. On the other hand, when requests come in, this is a multi-tenant system. We have many different customers or our own workload running on this entire cluster. So we need to have rate limiting to do some managing of how much load each request gets and each customer gets. And we also may have some capacity management, which will look at this entire system holistically, collect signals, and decide whether to scale up or scale down and tell the autoscaler to orchestrate the request. And this is what we call the control plane. So as a request comes in, it first goes through the rate limiter and gets routed to the data plane, and then the router in the data plane will send it to the model and the specific pods according to the routing algorithm. So as we can see, a lot of these parts in the multi-tenant system requires a good way to estimate how much load it is. And there are some obvious load signals that we can imagine, but that may not satisfy our requirements. For example, if we look at request counts, it is not a really good load signal because in LLM serving, each request may have different shapes, input, output, cache hit rate. So if you don't account for how much it request cost, then this is not a good signal because 10 very short requests is definitely less expensive than a very long 1 million input tokens request. On the other hand, if you look into the engine itself does provide some metrics for you. For example, when requests get into the engine and there are a lot of running requests that are saturating the KB cache, you might get the requests that are queued in the engine. But the queue depth itself may also be not a great load signal because it may be reacting too late to the incoming burst of workload. And when you finally scale up, it may already be too late. Resource usage also isn't great. For example, CPU, GPU utilization or memory utilization itself isn't a great signal about how much request is coming in and how much headroom you still have. So on this end, we need a good way to estimate request load. And the way we think about this is if we assume that there is a total number of throughputs, number of requests that can run per minute on this GPU deployment, then each request will have a share of the server throughput, and we will call this the request cost. Whenever we bring up a new model on a new type of hardware, we do an offline sweeping based on different input and output shapes, and we get the throughput of each shape so that we know an estimation of, for example, a batch of requests that have this input and output shape may have this throughput. So each request may have some kind of shares of this entire throughput. So during online serving, as new requests come in, we keep accumulating this, or when requests come in or after requests complete, they are removed from the accumulated costs so that we know when to scale up, scale down, or do some rate limiting based on the currently running requests. However, any kind of cost model is not comprehensive, and the cost model would definitely keep changing. The actual cost of a request may be drift from the request that was initially benchmarked. For example, if you serve GPT OSS and you increase the throughput or latency of it, and it is some significant optimization, then apparently with the same input and output shape, the request will complete more faster and you can run more requests at the same time. So this means that the cost model is you're overestimating the cost. On the other hand, multimodal requests with its CPU overhead and visual encoder overhead, it may cost more than what you initially estimated based on just the text-only data. Other factors such as prefix hash hit and mixed batch also will affect the actual cost. So request cost is just a prior that you can feed into the system. We need to keep updating it, and we can rely on it alone to do all the scaling decisions or like rate limiting. So going back to the engine part, we can talk about engine a little bit. So here I pasted some screenshots to show how fast the road is evolving across the engines. One of it is SGLang's release, one of it is VLM's release, and another is the scale of models that the number of models that come up every week. So with these kind of bi-weekly or even weekly changes to the engine road and the models we are going to support, there is a huge service area that we need to be testing. But testing alone may not be enough. So we need to have reliability around the entire system to make sure that anything wrong in the engine doesn't bring down the entire system. Typically, an inference engine such as VLM or SGLang is a multi-process system, and it is really easy to have some parts of the system, for example, one of the process to be down due to some query of death. The query of death is a term that these are some queries that bring some bad patterns of the system that crashes parts of the system and make it start hanging. And these kind of irregular workloads is not something that you can typically have a full test coverage about. This may be something that you didn't predict. It can be some sort of multimodal patterns. It can be some sort of grammar patterns that cause parts of the inference engine to fail. So if you start an engine, it crashes, it's very easy to catch. But what if the engine is silently failing, but you can't tell it from the outside? So the way we detect it is super simple. This is just a health check request. We just send a hi to the engine as a black box and as long as it returns a token, we know that it is working. So we build a very thin layer across all of the engines that we support and make sure that this layer can do all the reliability checks, such as health checks here, and provide the signals we need. One caveat of this is that we need to make sure that this kind of health check request is of the highest priority. Otherwise, if the health check just times out during when the server is having a very high load, it is not a break signal, it is a false positive, and we will just restart the server and it just keep crashing despite there is nothing really going wrong, just a high load. So with this mechanism, we can leverage Kubernetes' own health check and readiness checks and restart on failures so that we can recover this kind of query of death within minutes. And as engineers, we can decide whether to roll back or make some patches for hotfix offline without the production system really going wrong or the customer really noticing a huge failure. So we talked about the entire multi-serving infra a little bit. We also talked about the engine itself. And as a whole system, these two components or all of the components in the system is actually highly coupled, and it's very likely that stability can go wrong when certain components are under load, and it may cause cascading failures. So let's look at an example here. For example, if some of the requests cost much more than predicted, such as multimodal requests, then we will have the control plane services such as the rate limiter, the capacity management, assume the servers can take more load. So the rate limiter lets the request come in and the autoscaler does not make decisions to scale up the pods. So there are more loads hitting our inference engines than expected. Then we will see that in the inference engines, latency keep rising from like seconds to minutes, and eventually you will see some requests being queued up as the KB cache being saturated. You will also see some requests reaching timeouts that doesn't satisfy the SLA. And then the client or our batch inference service may just need to retry and send the same request over and over again, adding even more load to the system. And this will become more severe over time and cause cascading failure. There are several parts in this entire graph that can be improved to break this entire loop. For example, what if we just adjust the cost model so that the request cost can actually be similar to the predicted cost? By doing this, we need to do more benchmarks when more modality we support or different patterns or different like grammar or tool calling patterns show up. Then we need to address these additional overhead by addressing the cost model and increasing or decreasing the request cost. And this is something that is very feasible for certain things that are deterministic, but there may be some unexpected changes that may cause request costs to be different than predicted. So we also need more robust mechanisms to detect this. Also very generic way and also very useful way to do this is have some load shedding to break the loop. When we see that requests are queuing or timing out, we can just raise 429 errors to the control plane saying that we are currently under a high load and 429 errors being that is we are going to rate limit it. Then in this sense, the control plane can adjust the load, either not sending as much requests to the serving engine or decide to scale up. We can also cancel some requests that didn't actually reach the be running and are just queuing, and make sure that they can be scheduled again so that this time the serving engine doesn't have as much load to process. But any of those mechanisms doesn't actually change the actual issue, which is why did the request cost much more than predicted in the first place? Sometimes it's something you need to improve in the cost model, but sometimes it's your GPUs actually sitting idle and the overhead is elsewhere. This was a case when we were supporting multimodal requests at first. At that time, for some models in Hugging Face, there is a slow image processor that was enabled by default, which is backed by Pillow. There's also the fast image processor based on Torch Vision, which should be faster in theory. But when we enabled fast image processor, it suddenly became much slower and the overload issue just became worse. And the reason was that is actually because when we split the entire GPU node of 8 GPUs into several different pods for like 1 GPU per node, we need to set the containers to have the OpenMP number of threads correctly. Otherwise, it will cause CPU throttling for Torch Vision. After we fix this issue by doing some CPU profiling to find the root cause, we could just see that the request per second 3x after we deployed the fix. So sometimes we just need to look into what is the actual bottleneck and fix the issue accordingly. And then it will help the entire system alleviate the load. So here I talked about the 3 aspects, the capacity of thinking about a multi-tenant serving system and engine hardening itself and how these components may work together. So my takeaway to building a reliable LLM serving infra are 3. First, when building the infra itself, we need to build from first principles. And we might not expect it to work perfectly when the production workflows and paradigm shifts happen. We need to keep iterating based on new paradigms, new workloads, etc. Second, we also need to build safety nets for the unpredictable so that we can maintain shipping velocity, but also maintain reliability. Lastly, we should always understand the system as a whole. For people who work on engines, we might not care about the entire serving infra that much, but sometimes this can cause a huger problem than engine slowness. On the other hand, if we work on infra, we might not care about what actually is going on in the engine that is causing the bottleneck. So we need to also be able to pinpoint these things. And sometimes these can be the solution to a system's problem as well. So here is what I have. Happy to take any questions.
Ying, for the great presentation and lots of interesting learnings that you share there. I'll start with my own question here. A fascinating journey. I didn't even know Databricks got into this business, by the way, until recently from some of your blog. So that's great. That sounds like you guys are already, handling a lot of businesses. 125 trillion tokens per month. That's crazy. Do you support all kinds of models or certain kinds of model at the moment? What is that like?
So right now we support some Quen models, GPT OSS. We are also bringing up new models for potentially this or next week. So
Yeah.
stay tuned for the news.
Okay. There's always new models coming down the pipeline.
Yes.
In terms of the journey, how long did it take? If I missed that, I'm sorry, but just curious because it's a huge endeavor, right? This is like a very complex system, multi-layers and everything. So,
Yeah, a lot of these things were even built before I joined the team. Things like evolve a lot during the history. So first it was like not even a multi-tenant system. And then people in the team built a multi-tenant system to make sure that we can have more GPU utilizations as there are like more customers. So this was one thing. And the reliability battle itself is also something we like kept learning from.
yeah,
So
yeah.
that was like at least 1 or 2 years.
Wow. Okay, gotcha. I see one question from the audience. I'll bring it up. How do you handle cold start problem in production stage?
Oh, interesting. Can you clarify what do you mean by the cold start problem?
Yeah, I was curious about that too. Um, hopefully they're still around, but while we're waiting for that, so what's next for you guys now that you guys have it in production? What was the next phase?
Yeah, so there are a lot of things that are coming, like Kimi and GLM 5.2
Mm,
has all the buzz nowadays. So we're also doing like more large scale serving. So previously I didn't really cover the disaggregated serving, although that was part of the like router in the picture.
yeah,
So that is one thing. And we are also like trying to get more capacity so that we can serve more demands because there are a lot of like internal and external use cases that we want to support.
got you. Okay, I think that that person reposed a question. Let me bring it up. How do you find where the bottleneck is during production level inference, whether it's CPU, GPUs, or Kubernetes?
Yeah, first of all, we need to have very good observability and also very good logging. So if we have good logging, we can typically just do a profiling. We can know in the trace to see where the request starts, where is it in the running queue, or is it already running, or does it even get into the engine? So once you have the good traces, it's typically something we can know that is where the signal is. Yeah.
Okay, I see. Um, so now that you have customer, obviously 125 trillion tokens a month, um, how are you guys thinking about competing with the other inference providers? It's a crowded space.
Yes. What's Yeah, we're definitely thinking about this a lot. Um, but I don't know if there are things that is like interesting to the audience
Well, I
because
think the Databricks has an advantage in a way because Databricks has lots of customers or enterprises as
yeah,
customers. So
yes.
there's already established relationship. So it's probably easier to sell into those existing customer base.
Yeah, there are a lot of trends. So for existing customers, we are building like AI gateway. That was a huge announcement in
Mm,
our Data AI Summit recently. We're building this governance layer so that people can not only just use like Databricks hosted models, or they can also like point their Anthropic or OpenAI models to here and get the governance. We're
mhm.
also like trying to improve on performance optimizations a lot. So that's also a trend that we're like competing against like the inference providers.
Yeah. All right. Another question came in regarding the cost estimation of a request. What are some of the strategies that we can use to do that?
Yeah, so offline benchmarking is a really good source. You can get actual data when you run on GPUs and on your actual engine with your actual version. For example, different versions may have variance. And this is a good starting point. And after that, there are several things that you can do. First of all, whether you want to estimate the output, like output tokens is one thing. If you don't do that, sometimes it can be a huge variance to the system. So if you have good previous workloads, previous patterns, you can derive some heuristics or linear out like regression models to do that as well.
Gotcha. Okay. Um, so I'm gonna bring back a question, which is a good question, and I think you heard it when you were in the backstage, which is about um, how to get a job as LM inference
Well,
engineer. You've been in this space, so hopefully you can provide some tips for this listener.
I think that is a really good question. I feel like this is actually pretty hard. Yeah, because I feel like learning is important,
Uh,
definitely, and like being able to contribute to like popular open source projects, whether you're focusing on the engine itself or caching or multimodal, there are a lot of things you can do. Even like orchestration, Dynamo is also a great place to contribute.
Yeah.
But these are also like if you are just contributing open source, you also don't have the production experience.
Right.
I think the easiest is doing team transfers. If your company already have an inference team and
Mhm.
you also are a strong contributor, not only your team, but also in open source projects, then this is a great conversation to have.
Yeah, if you're fortunate enough, like you work in a company that they have an inference team, that's probably the easiest way to get in to learn and build your experience and then go from there. I agree with that. But if not all companies have that, unfortunately. So that will require a bit more work to get a job in this space.
Yeah. But even like having a really solid contribution in open source, that
Yeah,
could also be a great starting point.
absolutely. It'll be a good starting point. All right, Ying, thank you so much for taking time out and share with us some of the journeys and learnings from Databricks. So appreciate it.
Yeah. Thanks for hosting.